Welcome, everybody, to Dallas Personal Robotics Group. We're Robot Builders Night Virtual for February 24th. Tonight, we will do our normal presentation by roboticists and then sort of open it up to any discussions we'd like to have. If you have questions, feel free to ask. A little bit of housekeeping. In May 2026, we have our Roboama competition. Highlights from that are going to be quick trip, the line following advanced, the barrel racing, the 6-can, the 4-square, and the sumo. The rules for the competitions can be found on our website. I don't have the link right now, but they can be found there. And as well, next Saturday on the 28th, we will be holding our monthly meeting for February at the Dallas Makerspace at 10 a.m. Central Time, your local time in Dallas. Agenda is going to be show and tell, bring your robots to exhibit, demo, talk about, swap meet if you have anything you want to trade, get rid of your junk and maybe get some new junk for it. And Robbie, repair and upgrade, brainstorming and planning. We propose to start up a maybe bi-weekly in-person work meeting to repair and upgrade Robbie. Ideas and help are welcome for anyone wanting to make them even cooler. So think about that. They'll have a brainstorming session and looking for some volunteers, I'm guessing. With that, I guess we will start our presentations with Ray.
Okay. Let me see if I can get this to work. Okay. All right. Screen. Tab. Yeah, I can try the entire screen. Nope, that did not do what I wanted. Okay, I'm going to just do a window. Tab. And okay, that one. There we go. Come on. Okay, can you see that?
Yes.
Mm-hmm. Yeah, this was an article that I saw, and you guys may have seen it as well. It's kind of another method of making printed circuit boards, and it actually uses, like a 3D printer and copper foil tape to actually make the printed circuit board. So there was kind of a presentation a little while ago about a similar method to do this. In that method, the traces were raised, and you actually rub the copper tape on, whatever material you 3D printed. I think some people use PLA, others used ABS, and then you, with a razor or like an X-Acto knife, you cut out the traces. This one is kind of the opposite of that. You actually have depressions in the 3D printed base that you actually press the copper foil into, and then you sand off the raised areas, and it should leave your traces behind. And so that was, let's see if I can show some of the things in this article, and it's not scrolling. Oh, guess that's all I can do with that. Oh, let's see here. Try scrolling and zooming. Okay. Right. Look like I can scroll it. That's weird. Don't know why I can't do that. Okay. So the other thing, the other part of this, oh, maybe I have to scroll it in the original. Let's see here.
That's working.
Okay. Yeah. That's weird. Okay. So you can kind of see the two halves of the board, and this is after it's been sanded, but this is the one with that makes the depressions on this board that has the copper foil tape stuck to it. And then the raised areas, which would be like this or this, actually gets sanded off. And so they're saying basically the process is use any SVG or let's see, is it SVG? Yeah, I think it's SVG. Yeah, SVG editor, like Inkscape or something like that, to actually create the layout, and then you put, your SVG file into PCB Forge, and it helps you create, the two halves of this board. And there is a little video on how to do it here. Let's see if this works. Short. I think one of the limitations on this is I think the narrowest trace you can do is 2 millimeters, which isn't too bad. So this is applying the tape.
Yeah, I'm not seeing the video playing.
And that's switching it into the different areas. And then sanding it off.
Yeah, we're not seeing a video at all here, Ray.
Oh, you're not? Oh, darn. Sorry, I thought you were. Hold on. Can you see that?
Nope.
Nope.
Is it opening up in a different window?
I think it is, yeah. Okay. Presenting. Let's see here. Whoops. And okay, yeah, I think that's the one that I actually wanted to show. Can you see that? Is it playing the video?
Yes.
Okay. It just has for some reason, there's no sound with it. I don't know why. Anyway, so basically do your layout, import it into PCB Forge. It creates the two halves of basically a mold, kind of like a negative and a positive. And you stick the copper foil tape on it and use the other half to kind of press it in. And then you sand off the raised portions. And that's the part that you want to remove. And so basically the printed circuit board material, or the copper, is in like valley areas that didn't get sanded off. I think it's playing over again. Yeah, it is. So one of the limitations they said with this is that I think the minimum trace width you can do is 2 millimeters in width. So if that works out. Anyway, thought it was kind of neat. Seems pretty fast.
Yeah, I wonder how well it how soldering works with it. You know, I would
Yeah.
think it would,
I don't. Yeah, I know if you solder too long on, well, you know, it's just like an adhesive back
yeah.
copper tape. You can deteriorate the adhesive.
Well,
was
melt the plastic.
Probably not great
Yeah,
for
how about the
PLA.
PLA you printed it in?
Yeah.
Oh yeah, they said if you apply too much heat to it, you can melt it. So yeah. So it might be better to use ABS for that because it, you know, it's got a higher melting temperature. I don't know. It's maybe a technique you learn as you go, because if you apply too much heat, you melt the printed circuit board and make a real mess out of it.
Yeah.
Anyway,
But that's cool. I never realized you could get self-adhesive copper tape where the adhesive was also conductive.
yeah, I saw that.
That's kind of cool.
Yeah, I don't know how conductive it is. I mean, you might want to
Yeah.
solder between strips of the paint, you know, to ensure that you're getting, you know, conduction across tape boundaries maybe or something.
Right.
In
I
the old
actually
days,
used
for
it.
alarm systems, they used to use copper foil tape on windows, and it was conductive with the glue.
Oh, okay. So what was that used for?
Right.
It was used for, I don't know if it was to detect a broken glass,
Yeah, it was broken glass.
Huh.
so that
When you scattered it,
the
that
tape
stuff
was easy to
was
rip,
yeah.
but the glue was conductive on it. So when you turned a corner and you did a 90-degree overlap and you turned the corner.
We used it to seal up literally mil-spec assemblies on the test bench to worry about electromagnetic compatibility back in the 80s.
Yep.
Join two plates together and you make a nice little RF
We're
enclosure.
talking mil spec. What does he know about all that? That's what I'm saying.
Yeah, it's been a while. I did know spec though, Harold.
I know you did, buddy. I know you did.
Not anymore.
There's a roll of the stuff they used to put on windows. Adhesive on one side. I wish I had it wider. I'd try that little project.
It's really handy. I think they also use it in dollhouses to light the wires in the to wire up the lights in the walls.
I could make printed circuit boards if a 1/4-inch wide trace was okay.
There you go. Just use them directly, just really fat ones.
Really big circuit board.
Technically, it would be surface mount.
Kind of, yeah.
Yeah. Who needs the 3D printed part? Just put it on by hand and cut it out.
Anyway, seemed kind of neat. Obviously it's, you know, for simpler boards, like, you know, I think they said in the article, you're not going to do a 4-layer high-speed, you know, board for an FPGA or something, you know, that'd never work. But, you know, yeah, for simple stuff,
Now,
might be kind of quick.
I was just trying to scan through the article while you were talking. I didn't see how they're handling holes for through-hole devices. Does the 3D printer print the holes? I mean, unprint the holes?
I think it prints like a little nib that that gets sanded off.
Oh, okay. And then I guess you
So-
still
and
have to take a drill to it.
Yeah.
Well, it looked like there was a hole in that 3D print that they were showing, but
Yeah, I could.
I'm guessing one side would have holes, one side would have little pins, maybe.
Yeah, I thought that's
That
how they
makes
did it.
sense. Okay.
Yeah, and so the copper tape on the nib would get sanded off. That would be your hole. Maybe, I don't know. That seems kind of weird. Then you'd have to drill out the nib somehow. Maybe you do that from the backside or something. Don't know. But
Ed mentioned to use copper tape to shield RF inside of electric guitars. I would never even would have thought of that.
Yeah, I saw a little bit of a squirrel where it's on a stream last night, and one of my members, they shoot me all kinds of fun stuff that we should go do, and one of them for $230 already put together Tesla coil that'll shoot 11.5, 12 inches worth of arc. I'm like, cool. And then they claimed, they get this, they claimed you can control it wirelessly. As soon as that arc goes off, man, as soon as their arc goes off, exactly how is that little bitty battery hanging out in your controller going to control anything? Going to make it past all that?
Well, you can turn it on, Harold. You just can't turn
Yeah.
it off.
Yeah.
Once the clamp's on, it's done till it discharges.
And the funny thing was, it's like, and I was saying all that, and I said, yeah, I could take that to the office and turn it on, and we just all leave. You know, I can shut everybody down because ain't nobody gonna do nothing. And about that time, the one of the VPs joined in. That's also a member of my dev team on a project I'm on. He happened to join about the same time. I said, Tesla coil, jump, take it up to the office, turn it on, and shut everybody down. And he's like, please don't. Please don't. I'm like, man, I would not do that. At least not tomorrow. You know?
About 5-7 years ago, I was working on a transformer. So 12.8 kV down to 600 volts.
Mm-hmm.
And when we opened up the primary section in the transformer, we could see copper arcing, copper splatter on the side.
Oh,
Well,
no.
the side of the compartment was 13 inches away from the copper bar, and 12,000 volts can jump 1 inch.
Yeah.
So we
Okay.
figured it was a little bit more than 12,000 volts that arced to the side steel panel.
That,
We
that
figured
worked.
that hit by lightning.
So you're saying 12,000 volts, basically 12,000 volts per inch that it jumps. So if I'm talking here 12 inches, I'm talking here 144,000 volts. Does my math?
I would, yeah, approximately, I'm guessing.
That's a lot of V's, man. Okay, I'm sorry I got in the way. It just squirreled away, and I will shut up now. I got to go pick some stuff off the printer. I'll shut up now.
actually, I think you can start an arc at a shorter distance and then separate the electrodes, and it'll grow quite a bit.
Once you ionize the air, yes, but to get that air ionized is a lot.
Yeah, and the some of the high voltage switches actually used to, blast out compressed air to blow the arc out. So, and that was a way of turning it
There's
off.
all sorts of tricks they use with that. A collapsing magnetic field when you open the contacts helps push the arc away, so that to make it longer to go between the electrode.
Oh, okay, yeah.
contacts.
Yeah. Huh.
All sorts of things, like a magnetic coil. All sorts of things they've used.
Yeah.
What's the chemical? Hexa something fluoride or whatever, I forget. So contacts in a chamber with the gas. The gas is deadly, but it's very good at extinguishing arcs. There's all sorts of tricks they use to, if you gotta break a contact really, really fast, well, you need a way to extinguish an arc.
Mm-hmm. Yeah,
Okay.
12,000 volts, I think, would be probably lethal. I imagine it's very low current, but I
It
don't
was
think
locked
I'd
out
do
and
it.
grounded when I went in.
Oh, yeah.
Yeah, I don't. You don't play with that stuff at all.
As a controls engineer in industrial plants, I learned to stay away from that.
Oh, as an electrical supervisor, I had to crawl into those. So you're often the guy that's in there with the electricians working on, what's going wrong in here. So you're tested, you're suited up, you're everything. Okay.
When I first started, I was given a set of electrical locks, Pat. Never, ever had to use them.
Oh, God. I have all my life. So that's why I enjoy the programming way more. It's easier. And very rarely do I lock out to jump on a line. Any other questions for Ray?
Hmm.
Okay, Kyle, are you ready?
Yes, I am. Hello. So, let's see if we can present this. Let's do this window. Okay. So one of the things I've been working on was this. So I have this robot arm here that I got cheap off of AliExpress. I haven't touched it in a while, but one of the things that I found that was interesting in the robotics interest, in the robotics industry is a lot of them are working from the a lot of them are working from the ground up, as in a lot of them are trying to like get into that like sort of humanoid where they start like with the legs and then they do like the full body and then they work with the manipulators, which is why you see like a lot of them doing like for like the Boston Dynamics Unitree, they're doing like crazy backflips and stuff, but they don't have any manipulators, don't have any hands to actually do like useful work. Whereas I think the industry should be going the other way around, which they should be starting with like the very point that does work, which is the hands. So what I've been trying to design is this super cost-effective sort of like haptic system to give this cheap robot claw a sense of touch. So what I've discovered is if you know those microcontrollers that have this sort of anti-static foam, this is what this black thing is right here. And there's this unique property with this anti-static foam that when you squeeze it, it changes the resistance inside. What you can do is you can measure that. So I have a copper plate right here, soldered to a wire, and then I added another copper plate, and then I added some electrical tape on the end to isolate the wires and just like seal it off. And then I added a little latex glove finger just so it can be all like concealed like this, so that when you squeeze those two plates together, the 2 points become closer together, change the resistance, and then you can measure that with a voltage divider. And then that can be read through an Arduino or an ESP32 to measure how hard it's pressing down. So right here, you can see this is with it being relaxed, as in no force at all. And then this is with it being like pressed down hard, where you can see the values have increased greatly. But yeah, that's it for now.
That's kind of interesting. So the resistance increases when you push it down?
The resistance actually decreases. This is I think this is sort of an adjusted value, but you'll be correct. The resistance decreases as you
push it down.
squeeze it harder.
Yeah.
The thing is, like, it's in sort of like mega ohms, and then it drops down to like 200 kilo ohms. But the range is like so great that you kind of have to use a voltage divider and then like sort of adjust the value so it's something that's actually readable. So I thought it's kind of cool to create this at like such a low cost. I mean, like this entire module handmade, I bet it would cost like less than 50 cents or maybe even less than 25 cents to make. I mean, it's just a small piece of foam, some copper plating, and then just wires, and that's it. So very cheap to make. The reason why the industry doesn't use it that much is because the one drawback with this is it's kind of like memory foam, where if you squeeze it down for long enough, it'll kind of stay there for a while and then slowly go out. And of course, that's not great for like precision, especially for like high speed applications. But like my goal with this was just to create an as low cost as possible sort of force sensing system. and I think I've done that well. If I engineered like some like crazy like $5,000 Woji hand or something advanced like that, having something like that will be a bit overkill for this like really low budget sort of like AliExpress robot arm. But yeah, I think it fits it well.
How much force are you sensing there, and can you tune that?
So I'm not sure how to answer this question, but what I do know is the force is sort of so the force pretty much is measuring the or the resistance is based on the distance between the two pads. So if you have, say, a thicker pad of the anti-static foam, that'll give a different resistance value than if you had it much smaller.
Okay.
I'm not sure if that answers your question.
I'm just asking because I'm kind of interested in if you can get it so it can sense like a light touch, you know, touch something real lightly, or does it require a lot of force to?
Yeah, so the idea with this was, so I did have some of those sort of capacitive, like sort of touch sensors, but those again are just on and off that you can like sort of measure how hard it is. So like if I did like a light, if I just like press it lightly, it would go from 350 to around 425, 450. And if I press it really hard, then it would go to these figures here, closer to 800 or 775. So yeah.
Okay.
So it's kind of
Nice.
relative, I guess. You don't know the absolute force or whatever at this point, but yeah, you could probably figure it out maybe with strain gauges or something.
I mean, right now it like just requires manual calibration, but which isn't always the most fun. But when the main constraint is cost, I think I've done well.
Yeah.
Yeah.
You can sort of grab an egg and see when it breaks.
That's a good
Yeah.
benchmark.
Yeah, I think the other thing with the foam is it may vary quite a bit with temperature and humidity. So it may need to calibrate it just before you use it for whatever environmental situation it's in.
What I could do is have like a so like when it starts, it can have like a pre-calibration program. How would that work? I don't know, but I mean, again, the motors themselves are just the standard hobby servos, so they don't have any, by themselves, they don't have any positioning feedback. They don't have any sort of like current feedback, so you can't like measure. A lot of robots in modern robotics they measure how much current the motors are pulling, and that can be measured by how much force is being applied to the object, which is a much more precise alternative to highway here. But yeah. So the next steps, I think the biggest thing I was having trouble with is sort of mounting it. So right here, I'm not sure if it's visible. So right here is the module, this little finger. For just a quick makeshift solution, I kind of just hot glued it right there, or on the inside, excuse me. But it's, I mean, of course, like mechanically, like not really accurate or well done. I guess I'll just have to 3D print them out, but that's pretty much it.
It's great.
Thank you.
Yeah. I'm going to see it develop. It's great. Yeah.
Yep. Hopefully I'll be able to present something this DPRG month, this Saturday.
Bring an egg. Yeah.
Yeah.
Not hard boiled.
Yeah.
Well, thanks, Kyle. That was interesting.
Certainly.
Next up, we have Mike.
Yeah. So I've been wrapping up that project.
Kyle, you're still presenting. Sorry.
Can you unpresent someone, or do they have to do it?
No, I can remove him from the call, but
Oh, yeah.
Well, there Mike's presenting, I think.
Yeah.
I think Mike just took over.
Yeah. I just took it. See. So I've been working on I got it running, and I'm working on my GitHub documentation. Got more to do, but tomorrow morning, early in the morning, I go to Chicago for 2 weeks, and I needed to get this done before that, but I got it done.
Oh,
Okay,
I see
so-
the login and password. Can I take it over?
Sure, if you're close enough to get the Wi-Fi signal. Yeah, and
Oops.
so basically, the way you do it is you configure it, and then you press you have to home it first. So you press the home button, and then it runs a little homing sequence, and then when it's done with it, it's pointing in the direction that you wanted it to point. And after the homing is complete, then you press the run button, and it starts the periodic rotations. So the important thing was the periodic rotations had to start precisely at an interval. So there couldn't be any, what do you call it? Creep. So basically one 10 minutes, 10 minutes, 10 minutes, and not have any drift, I guess. So that's what it does, and I simplified it a little bit. So this is the this is what it looks like, where the business end of it is. So basically, this is a motor, and you can't see it here, but there's a drive wheel here, and these are the 4 casters, and this is the limit switches to know what position the platform is in, and I'm running power through here, and it comes out to the top of the platform and rotates. And so this assembly here is for the power to come up and mounts this bearing. And the bearing is there. It's not really a load bearing. It's just to keep it centered. And then this is the motor controller right here. And of course, power strip. And so this is this is what goes on top of it. And so you have this is what the bearing slips into here, and this just keeps it centered so it doesn't drift, and so it stays centered on top of the lower platform. And then these are the limit switch. These things hit the limit switch. There's 2 limit switches. One is the home switch, and one is just is every 90 degrees, except for the home. So 2 of them. And then one of them is the home. I think it's this one here. I think that's that one. It looks like it's the furthest one away. And so when it rotates, then this one will hit every complete rotation, and these hit on the other at 90 degrees. So that was, they didn't need a lot of precise, or it just goes, 180 or 360 or something like that. So this worked really good. So this is the side view here, where you got the motor, and then this is the drive wheel that actually, this one here has the friction that makes the upper platform rotate, and these here just rotate freely. And then of course you can see here, this is the bearing that gets centered into that collar here, and the AC power goes to this hole. And And then the trick is like these wheels are all basically the same height as this wheel here, but this one needs to be up just a tiny bit just to get the friction, to get some drive. And so you don't really know what that is until you put it all together, and then you need to adjust the height of that wheel. And so to adjust the height of that wheel, I just adjust these 1 or 2 turns to raise it up, a millimeter or so it gets a little more friction. So if I need more friction, I can turn the bolts again and raise it up some more. And that worked really good. I've had to do a couple adjustments to get it working well, but that works really good. This is the motor control unit right here that sets the speed. And tonight I had demoed it with the artists, and they wanted it in this range here. So I should have bought a motor with more reduction so that so we could run in this mode here. But it's good enough. It's not really super precise how fast it runs. It's just sort of a feel. What's real precise is it has to start the rotation very precisely, because the videos that are going to be playing are on a loop, and this thing has to just precisely time the same loop as the videos, and there's no way to adjust it. That's the way they wanted to do it. And then I can't really see it here, but this is the microcontroller with a USB cable that uses it for power. This is the ESP32 module. And then this right here is the solid state relay. And this switch here configures the speed controller to be clockwise or counterclockwise. So clockwise and counterclockwise. It's like, which direction do you want it to go? So that's sort of what you do, is you give them all the choices so they can figure out what they want. And so I made a web page. I put the ESP in AT mode, which it's given out at the top, the SSID and the password. And then it throws up a web page. And this is the top of the web page where you configure the stuff. So one thing is when it homes and it's finished homing, then second, you go on here. I guess. So if you have it 0, then the top platform will be lined up with this in the home position. And then if you set it non-zero, then you can set the angle, so that you can have a little offset on here. Like if it's not pointing exactly the way they want it to go, and you don't want to move the whole object, you can just fine tune it in software to say, okay, I want the video pointing 2 degrees this way or 3 degrees that way. So, or 10 degrees or 45 degrees. So that's what that one is for. And then the other one is pretty obvious. It's the period of the rotations, and it can go from 60 to 1,000 seconds. I figured 15 minutes is what they want max, but if they need to, I can change the software. And then this is a list of degrees. So you can go like 90 degrees, 180, 270, 360. And so every time it has a periodic rotation, it says, okay, trigger the periodic rotation, then it does this here. Yeah, it'll do it this many degrees offset from where you had it tuned from your homing position. So if you set your homing position to 45, then this will keep the angle relative to that 45. You'll just rotate a half a turn. And then of course this is the exciting commands. Of course you got motor tests, just turn the motor on, turn the motor off. So it's like, okay. And then this is like, what you do is you home it, wait till the homing sequence is done. Then you say, then there's just no way to synchronize with the video except start the video and hit the run button, and it's synchronized. So that's the way they want to do it. And this is my schematic right here. So basically, it's the ESP32 S2 module, and I'm using like three pins on it. One is to control the motor. So I wanted to just send ground out to the stuff and not power. So I used a PNP transistor and then drove it with an NPN. And so basically now, you get a nice control. And so basically when the width comes up, it comes off 0. And when it's 0, then this one's not conducting either. So when this one goes high, this one conducts. So so when it powers up, it powers up ground. So it doesn't power up with the motor running. That's always good. And then the switches coming in, I just ran about 5 volts and put the transistors in there and used pull-ups inside of here. And so the transistors do a level conversion. I could have sent 3 out there, but on these resistors. But the main part of these transistors, I could have hooked the pin directly to the pins here, but that's a little dangerous from an ESD, from static noise and stuff. So transistors like this are pretty robust. I probably should have put a resistor in series, but they're pretty robust. And of course, this is the S2 mini pinout. So that's my documentation now. I had some text in here between between the windows, and then in the platform control, basically. This is how you use it. So it worked really good today. We modeled up the statue, the sculpture that's going to be rotating with cardboard, just to get them a dimensional feeling for it. And then they say, "Oh, this is a good speed. Yeah, it works great." So now I can go out of town for 2 weeks, and when I come back, then we'll finish it up. One thing I'm going to go back to the beginning here, because this is what my Wi-Fi AP SSD and password shows up as. And the strange thing is that's the SSID and password for an earlier project I used on that same board, or an early version of this. And if I go to the code, let's see, code. I have the SSID set up as dichotomy and the password as passion, because this is the project. It's dichotomy of passion. And so if I follow this out, and during my initialization, during the setup, I set it up in AP mode, and then I set the AP address with that, but you remember this is this password and SSID, but it's actually coming up with an SSID and a password I used in an earlier code that I loaded onto that microcontroller. So that has me scratching my head, but hey, the other SSID and password works, but I'm still scratching my head. I was thinking maybe I've got to figure out how to just erase the EEPROM or something completely. Something storing in memory somewhere, and I'm not sure where. It's driving me nuts because I didn't go to the library and hard code anything. I hope I didn't.
ESP makes a ESP tool you can use to wipe out the flash and everything completely on the chips.
Yeah, that's what I'm thinking. Like, but I just don't understand how the library uses an old thing instead of this stuff that I'm sending it. So
yeah, that is
Okay, and another thing is last week I was reporting that, hey, I got platform IO to work, blah 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 blah, and so I started going to start running this project, and the way I want my complete project, my complete GitHub project is I wanted to put everything under Arduino underneath my workspace, where I save this whole workspace on GitHub, and it wasn't. I didn't have a way to say Platform IO project and then have all the code for Platform IO. I couldn't find a way to do that. It's wanted to go into the Platform IO folder where it was when you initialized the software. Oh, well, so I reverted back to Arduino. This is simple enough. So it's like, I just do Arduino.
Platform IO wants to use its project folder structure.
Yeah, and I said, I just want to put that project in here, but then it has a project folder structure that has all of the projects in one folder, and they're all subfolders of it. It's like, that's not the way I want to work. That's not my style. So I just went back to this where I can just put Arduino here and it's happy. Yeah. But so another thing I did is I sort of did something like what Ray does, where I have the I put together a description of what I wanted it to do.
Yep.
And it created the code. So I just did one with the on-off buttons. I said, oh, that works good. And then I created another more complicated one to add in all the other functionality. And that worked good. So basically, instead of recreating it from scratch, I could have done it, but I just said, update the existing code created with this file with this new one that adds more stuff to the original code on off. So that worked pretty good. But one thing it didn't do well is the thing about that. If we go back to the README file, let's see, preview. Get it. If you go back to the README file, remember I said here's the home offset, and then I said then the periodic rotations rotate relative to the home offset, and it couldn't quite figure that out. It would always rotate just to the 90-degree markers, like the limit switches, and it wouldn't do it couldn't figure out that it had to go this fraction, even though I told it. So I just did the coding myself. I didn't want to try to fight the AI to do what I wanted it to do. So, but I used Claude to do it, and it worked pretty good. So that's my show and tell.
So what piece of artwork goes on top of this thing? Do you know?
It's a sculpture of a house on top of a rocket on one side, and a house with a tree growing through it on the other side. And the whole thing's like 7 feet tall, 6 feet wide. Yeah.
Oops.
And then it rotates. So one side is like a chaotic with the rockets and stuff. And the other side is a peaceful house. And so that's where the dichotomy comes in. So so his thing is like there's a dichotomy. It's like, okay, some people have this as their normal, the bombs and stuff. The other one has white picket fences and stuff like that. So it's basically he's trying to represent that in a art gallery space. And this is supposed to give us some motion and draw people in just for the story. So that's all I got. Is anything else?
That's interesting.
Mike, you're showing that nice engraved control panel. How do you make that?
It came with the motor.
Came with the motor.
Oh, it came with the motor. Oh, okay.
I just mounted it and then
All right.
taped on the solid state relay to the side.
All right. Good. Good.
You
So this
throw
is the-
money at it. That's how.
Yeah. Yeah, this is the micro, and it runs. These are the control wires for it here for the solid state relay, and so it just shuts the power on for the motor. So it's pretty basic.
Interesting. Thanks, Mike.
Oh, okay, good. Stop sharing. I guess. Where am I?
Next up, we had Mark. You are muted, Mark.
Sorry about that. So I was going to do an update on just kind of what I showed last week. So last week, if you remember, I had the wheel that I was kind of playing around with. So this week I actually started developing a driver for it. So let me start up the control here real quick. So I have things like I can set it to half power. And so right now, all it's doing is just driving the motor. So if I come and grab the wheel, I can basically slow it down and put it under strain. But I also have a RPM mode where I can tell it to go, for example, 50 RPM. And now it'll control it in an RPM mode where it'll basically drive at a constant RPM. So now if I add strain, it'll actually maintain the speed. If I let go, it'll resume. So I've basically been working on the driver to get that working. So it uses a magnetic angle sensor to basically detect the angle of the wheel, and then uses that to calculate the RPM. And it just has a simple control loop to maintain the RPM.
So you're using like the NAS 5600 or something?
Yeah.
Yeah.
So if you look on the back side here,
Yep.
you can see the AS 5600 there.
Mark, did you write that code yourself, or is there a library for it?
For which?
The AS 5600 code that gives you speed and position information.
There's libraries out there, but I did write my own because it's fairly straightforward, just over the SPI interface.
Okay.
Or sorry, I2C.
I'm looking at using some as well for what I'm working on.
But yeah, there's several libraries for it, depending on what microcontroller you want to use.
Okay.
And they're pretty straightforward to use. And then I wrote I coded up the code to basically calculate the RPM. And then also the code to maintain the constant RPM.
Okay.
So, and then the idea is that this is going to be going into a robot. So I've been starting to work on that robot platform. So here's the where I've gotten so far with the platform so far. So just a simple 3D printed platform.
What reduction ratio is the cycloidal again?
No, this one isn't using a cycloidal.
Oh, it isn't.
No. So basically there's let me show you, it'd be easier from here. So if
It's
you
just
look,
like a spur gear and
you
a
look
pivot.
up front, it's basically a spur gear. And then the wheel's driven on the outside of the hub.
Oh, okay.
And so the motor itself has a reduction of about 30 to 1 on the gearbox on the motor. And then the wheel is about a 5 to 1. And so basically there's an outer gear that that's basically just driven, and that's on the bearing for the wheel.
Okay. Were you going to use the cycloidal reduction, or?
I was playing around with that for something else.
Oh, okay.
So sorry, I switched topics.
Oh, that's all right. They look the same, I guess, or look similar.
So yeah, so this is just using a simple motor and spur gear. So for the motors that I'm using on this robot, I wanted to keep it nice and lightweight, and spinning the cyclodal wouldn't work with those motors. So
Oh, it went, yeah.
Those motors are way too tiny for that.
Yeah, I had to measure RPM on my project. So basically I timed between the limit switches at 90 degrees. So that worked out pretty good. I mean, the AI didn't get the correct calculation. It couldn't figure that out. Poor AI. Because I needed it like I knew at the 90-degree angles where I stopped, but I wanted it to have offsets of somewhere between 0 and 90. So basically, I spin around and then I go hit the third 90-degree limit switch, and then I've measured the RPM, and I can know how many seconds to turn the motor on. So, yeah, mine's pretty brute force, simple. I guess yours has a nice PID loop, right?
What's that?
Yours has a
no
PID loop?
It has a P loop.
P, okay.
Right now it doesn't have. I haven't put in the I and the D yet.
Yeah. I usually just
and
do
I
P and
haven't
I.
even really tuned it all that well. So
yeah, I rarely use a differential. I always just use proportional and integral. Differential is really hard to use.
Yeah. I guess if you really need I guess it's like for a step, input, and if you really want your output to follow that step, that's
quickly. Yeah.
The D mode or D part of that will help, but it's
gives
also
gives a little oomph at the beginning. So
yeah. But your motors would probably last longer if you didn't use it, So.
Yeah.
So anyway, that's basically what I have.
Cool.
Anyone has any questions or anything?
So how much? It seems like you were grabbing the wheel pretty hard, and it had relatively a lot of force. So I guess it can have a lot of traction, right? Yeah.
What's that? Yeah, it actually.
You're grabbing the wheel pretty hard to slow it down, and yeah.
Yeah, it works pretty well. Even with the small in 20 motors.
Yeah, so it could go up hills and stuff. So yeah.
So did it let any smoke out of the motor when you did that, or no?
No, I have smoked one, but.
Ooh, seriously? Yeah.
I actually didn't smoke it. I actually just jammed the gearbox on it.
Oh.
Yeah.
Plastic gears, yeah.
No, they're metal.
Okay.
They're the little N20s. I'm sure you've seen them.
Yeah.
And
microscopic teeth on the gears, right?
Yeah, pretty much. Yeah. I thought I had one out here, but I don't. Oh, there it is. If we can get it out of its bag. So this is what I'm driving it with.
Whoa.
Yep. Pretty small.
Oh.
You're
Nice
way
small,
down.
tiny motor.
Yeah. 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 So I wouldn't do the differential on that one.
But that's the nice thing about when you 3D print everything. It's lightweight, so you can actually get away with motors like that.
Mhm. Yeah, you don't have to you don't have to move around and rotate a couple 100 pounds, so that's
Yeah.
good. Yeah.
Even when you are spinning a 5-inch tire.
Yeah. So what kind of tread you can put on the tires?
What's that?
What tread are you
They-
gonna put on them?
They have it's got a TPU tire on it.
Okay, okay. Ah, okay.
So basically,
Oh,
Yeah.
cool. So is there some sort of cleat or something that holds the tire from slipping, or do you glue
What's
it?
that?
Or is there like a cleat or some sort of catch on the inside of the rim and the tire to prevent it from
so
slipping?
on the rim, I basically have a raised center section that basically grips the tire and holds it. And there's just the stretchiness of the TPU holds it in place.
Oh, the friction. Yeah.
Yeah.
Hmm.
So you can see kind of the raised center portion there. And that basically goes into the tire has a matching recess on it.
Yep. Yeah.
Well, those should be able to grab cans and move them around. So good for 6-can.
Mm, yeah.
I'm planning on trying to do that.
Yeah.
I don't know if I'll make it, but that's what I'm going to try and do.
Yeah. You can see how well you tuned up the PID. I mean the RPMs and stuff to see if you can do a quick trip or a 4-corner with precision.
Yeah, we'll see.
Here's the earlier, much less sophisticated approach. It's a 3D printed wheel with a rubber band tire on it. So
Mm-hmm.
works actually pretty good. It doesn't stay centered, but it's got a little wiggle in it. But
Was there a groove to put the rubber band in?
nope, it's just sitting on there with tension. So
Okay.
A little higher, Ray, please.
oh, sorry.
Thanks.
So just a rubber band slapped on the 3D printed wheel. And this one actually has the the brim that you can use. This one, I left the brim on.
Yeah.
That's a nice, healthy gear motor you've got to drive that too, eh?
Oh yeah, those were
Wow.
one of a kind from one of the electronic companies like Tanner Electronics, Herbach and something. Anyway, I bought 2 of them, never saw them again for sale. So I may have the last 2 in existence. I don't know.
You can smoke the rubber bands by starting it real fast. Boom.
Yeah, there you go. Yeah, your TPU tires look a lot better than that thing did, but
Yeah, the only thing about TPU is I find it's a little bit slippery for a tire.
It depends on which CPU you use, but yeah.
Oh,
But it's
I didn't know
better
there were
than-
different
but
kinds
it's
of
better than
TPU.
PLA.
Yeah, for sure. Better than PLA.
So is there some sort of
rubber
solid
band.
rub on your TPU tires and make them, like really sticky.
There you
It
go.
also makes a difference too on if you go with a bigger tire similar to this one. You can actually vary the traction on it quite a bit by based off of how much infill you give it.
Mhm.
So, for example, this one is actually pretty soft because it's got very little infill in it.
Yeah, I suppose if you wanted to, you could spray something sticky on it or coat it in rubber cement or something.
Mm-hmm.
Just
Put
as
glue
long as
on it and roll it through sand.
that. So who's next? You're muted.
Can't hear you, Pat.
Yeah, you're muted.
Next up, we have Carl. Sorry.
Okay.
All right. So not anything robot-y tonight, but it's just, I thought, a remarkably well done little gadget. And this is a credit card sized phone holder, believe it or not. So you can stick it in your wallet. And then when it comes time to set your phone down, maybe at a restaurant or maybe out, take a selfie of photos or a tripod, you turn it like this and you fold that like that. And voila, you have a stand you can stick your phone in like so.
Hmm.
And it has quarter 20 mounts on it. And these things have, they kind of rotate so you can give it different angles and you can swap them out for different sized phones. But I was just really impressed with how well it was designed and made. You can even if you want, you can pull it apart and then use it as two separate legs for a wide thing. And then, of course, it's kind of fragile. You got to watch the way the joint is, but it just seems to be made so very well. And then these legs apparently have carbon fiber filling. But anyhow, we have gadgets now and then, and I'm always on the look for something to hold my phone when I'm at a restaurant or out trying to take photos or something. And it sits in the wallet. It's not that much thicker than one of those metal credit cards.
I have
Anyhow.
a 3D printed one, Carl. It's
Yeah.
something similar. It's not quite as robust, but it folds flat like that and folds up.
Yeah, they're super handy.
Yeah.
Nice.
I'll put the link in a minute. But if anybody's interested in that stuff, it's always on the lookout for a fancy new tool. And that's all I got. That and a cold.
Sorry for your cold. Hope you get better soon. Next up, we have Tom.
Oh, okay. Get some props here. Some of you may recall my efforts to build an outdoor robot. This was my second version, which runs really, really well in my nicely manicured backyard. But when I took it out to the battlefield park that we were going to use for the outdoor course, the ruts and the grass and the weeds, they kind of come up to the deck and above the deck, and the ruts are half the diameter of the wheel, and it's not powerful enough, although I thought it was powerful enough. So that was kind of a bummer. I wasn't very happy about that. But sitting in my junk collection, there are bigger wheels. So I thought I'll put some there. You can see the comparison. So I'll put some bigger wheels on a platform. And that might help with the rut problem and with the height problem. And then there's the issue of how do I power the thing? So I went looking through my other junk pile in my heavier duty workshop, and I found several of these, you may recall, vintage screwdrivers, electric screwdrivers. I have several of these. So
Black and Decker.
yeah, these were both Black and Decker. And then I have another off-brand, which was supposed to be a drill, but it wasn't even any good for screwdrivers, for screws. But these things, I have a motor tester I built a few years back, and I put them on my motor tester to get a feeling for how good they are. And they have a nice chuck on the end that normally holds a screwdriver. That's a convenient place to put a 3D printed hub to hold the wheel. I'd like to get some speed sensing. I will probably use an AS5600 and see what happens, since I can get at the back of both motors without too much trouble. And these things have reasonably good speed curve profiles that'll give me about 400 RPM at 5 volts. You don't want to push them much higher than that, but you can see the magnetic fields go into saturation up around 6 or 7 volts. So you probably don't want to run them much higher than that, but at their nominal rated values, these originally had 2.4 volts on them. They were a pair of NiCad cells. And they were supposed to be good for somewhere between 25 and 30 kilogram centimeters of torque. So my rough calculations for what I would need to run a 3 kilogram robot up a 30-degree slope is only about a third of that, split across 2 motors. So these things are probably a useful thing to experiment with. So that's sort of the current state of my fiddling around with a higher powered and larger wheelbase or larger clearance robot. We'll see where it takes us. These wheels are off of some kid's ride-em car. So since I had them, I figured I might as well use them. We'll see what happens. So that's the state of the art in what I'm trying to do with robots.
So how many wheels does it have? Does it have 2 wheels and a caster, or 4 wheels?
Well, I'm going to try 2 wheels and a caster. I'll have to design the caster to be quite large to be comparable with the clearance of the big wheels. I have a box full of random wheels that are pulled off different things. So I'll just use one of them and build a caster. I have casters, but they tend to be smaller. They only be an 1.5 or 2 inch wheels. I'll need a caster bigger than that to run it out of doors. If worst comes to worst, I have 4 of these wheels, and I'm in the process of gathering some more of these old screwdrivers, vintage screwdrivers. I put out a request on Facebook's Marketplace locally to see what happens. I've had 3 people respond in 8 hours, with one of them at a fair price. I mean, if I wanted to just buy a gear motor solution, I could spend $20 or $30 per unit and buy them off AliExpress. But I thought I would play around for a few bucks with these screwdriver gear motors, because they seem to be just the right size. So the right speed, and they've got enough torque, I think. So we'll find out. And I've been busy trying to get rid of stuff in my workshop, which I try to do once a year. And I'm finding out that a lot of the really, really old hardware and software I've got kicking around here is actually worth quite a bit of money. You guys may remember AT style keyboards with the big round DIN connectors on them. I had a collection of not very nice looking ones here. Somebody bought them all from me today.
Oh,
I couldn't believe it.
Yeah, the vintage computing people, man, they snap that kind of stuff up, dude.
I had one Microsoft 8-bit ISA connected bus mouse adapter. I didn't have the mouse, but I had the adapter board. I sold that for $40 plus shipping.
Yeah, that's catnip, man. That's catnip to those people. I'm telling you now.
Well, I got one more complete with 3 bus mice that go with it. So I'm just waiting for somebody to snap that up. That's how I'm funding my robot project.
There's a Go Build It makes a pretty nice.
Oh, I like that. Let me blow that up here.
Okay.
Oh yeah, that's what I want to build. Okay.
Yeah. I forget what it costs to go build but I put a plate on or 2 plates to extend it out a little bigger so I could, put a bigger wheel on it.
Does it have a bearing on the top to allow it to rotate, or do you have to make your own?
You have to make your own. They do have their, it's like a fill-in. It's made to mate. This is the size hole that's up here. I forget. Maybe 10 millimeters, maybe. Yeah, maybe longer.
Okay.
Or bigger.
When I run my motor tester on these motors, I get a nice set of curves out of it. And that's useful because I'm clearly going to have to put a bigger battery on this robot than I thought I would need. The current draw, even at 5 volts, is fairly noticeable compared to what I'm used to on small gear motors. So I may have to up the weight estimate of what my robot will weigh by the time I'm done.
Anyway, that's a 6-inch wheel.
Okay.
And you could probably go to a 7. There's enough clearance.
Yeah.
You know.
These are 8.
What?
And, these are 8-inch wheels.
Oh.
And so I'm thinking I'll probably need maybe a 4 or 5-inch caster.
Yeah.
Depending whether I put the gear motors on the top side or the bottom side of the platform. I can control that a little bit and see what size caster wheel I can get away with.
Yeah. This would accommodate an 8-inch wheel because I can go, 4 inches off too. Like right. Yep.
Okay.
Right there, and it still clears the top piece.
As long as my robot is dragging its caster wheel, I probably don't have to worry too much about the ruts on the caster wheel.
You'd have to worry about sticks getting stuck in there.
That's true. Yeah, you can always have that.
Yeah.
When I first looked at this Battlefield Park area that we were going to use, I thought, oh, this looks great. It's not that much different from my lawn. Oh, it's a hell of a lot different. They cut it with a farm tractor.
A bush hog, huh?
Yeah. And you do it when the ground's wet and it gets all ruddy.
Yeah, that's okay for the outdoor contest last year. Didn't really know what to expect as far as how well manicured Steve would have his lawn. As it turns out, he got a robot lawnmower and he was doing like crosshatch cutting on it, so it was like perfectly flat. Nothing stood up about more than a couple inches. And I didn't mow mine, and they're like long, basically seed pods that this one type of grass puts out. And
danger.
Yeah, it didn't like it at all. So I probably could have done a lot better at Steve's than I did at my own house. So. Kept thinking, yeah, I should have mowed that. Oh well.
That was it for our list of presenters.
Okay. Well, I gotta drop off and wake up early for my trip. So,
okay.
Good night.
I'm looking for somebody to host the meeting on Saturday. I will not be available.
I can't do it. Yeah.
So I've sent an email out to the board and see if somebody there can
Okay. All right.
host. I don't know if it's even going to be online, but we'll see.
All right. Good night.
Good night.
Does anyone else have something robot worthy to bring up? Well, going to be an early night then, guys. Stay safe, keep warm. And we'll see you, for me, next Tuesday. For the rest of you, maybe Saturday.
Okay, folks. Good night.
Good night.
Good night.